Remember that really on those you're looking for differentiability, continuity, because those are the things that can keep the MVT from working. I think we did. I thought we did 1 through 8 and then 15 through whatever. So which one are you talking about? Number 4? 5? All right, so 5 says, all right, I've got inverse sine. Well, you have to know what inverse sine looks like too, right? And that's kind of hard. Do y'all remember what those look like? This is what we're doing in pre-cal too. I gotta get out of, we hadn't made it into radians yet though. So inverse sine, the domain, remember inverses are x and y switched, right? So let's think, let me show you what that first. We didn't spend a long time doing sine before inverse sine in pre-cal, but let's go pi over 2. Just to graph sine. What's the sine of 0? 1. 1 or 0? Sine at 0. What's the y value at 0? 0. Then at pi over 2, it goes up to 1, right? So the sine graph does this. Yes? All right, this is sine. So now if I do inverse sine, that means I switch x and y, right? So instead of, so 0, 0 is still there. Instead of pi over 2, 1, it would be 1 pi over 2, right? So this thing is going to turn on its side. And do something like this, right? Do we all agree with that? But that's not a function if it keeps going forever, right? Because it doesn't pass the vertical line test. So for inverse sine, they're restricted. You cut them off from here to here. It's actually from -1 to, no, from pi over 2 to negative pi over 2. But it's cut off so that you have, so that it's completely, so that it retains its functionality is what I'm getting to. So if you graph it on your calculator, you'll just get this funky little piece of graph that looks like that. And that's exactly what it is that piece of curve. So I guess what I'm getting at here is, on this, it is continuous here on -1 to 1. It's still a function, -1 to 1. What else am I looking for? Say again? Differentiable. And yes, it's differentiable on that interval. Does that make sense? So now the question is, does it satisfy the hypothesis of the mean value theorem? Yes, because it's continuous, it's differentiable. Let's see. If it does, find each value c in the interval that satisfies. So what do I have to do? I have to show that the derivative equals I have to show that A rock equals I rock, or I have to find where it does. So what I'm going to do, find each value of C. So I'm going to find the endpoints here, right? F of -1 and F of 1. Now this says, where is the sine value -1? So you tell me on your, you're looking at me like I'm speaking a different language. Where is sine -1? Which is 3 pi over 2. Are y'all following me? Now, where is sine positive 1? Does the inverse change what? Well, so that's what, this is not, so it's not the sine of -1. It's, if you do inverse, it's where is sine -1. You see what I'm saying? Does that make a difference? So before I would say the sine of pi over 2 is 1. The inverse sine of positive 1 would be pi over 2. Okay. Where is sine 1? I just told you. Pi over 2. So now let's plug it in AROC, because really that's all I'm doing is I'm plugging it in AROC, right? And then setting the derivative equal to that, because where does AROC equal IROC? And that is the mean value theorem. Y'all understand? The slope of the secant line, the slope of the green line there, somewhere in between, at least one place, IROC's going to equal that slope. Somewhere there's a tan line that has the exact same slope. Y'all see that? Are you sure? Or are you just saying that? Are y'all just going this to get me to shut up? Somewhere, if you find 2 points on any function and it's continuous and differentiable, then the slope of the line that connects those 2 points, somewhere inside there's a tan line that has that same slope. It has to. That's the mean value theorem. That's all mean value theorem says. IROC equals AROC somewhere in an interval. Okay, so to know where it happens, let's first find AROC. Remember, this is AROC. This is IROC. I don't know where you rock. That's where we rock. Okay, shut up. Okay, let's do. Let's just carry right on. All right, AROC is 3 pi over 2 minus pi over 2 over -1 minus 1. 2 pi over 2, just pi, over -2, so negative pi over 2. You okay there? Agree, disagree? Now I need to find IROC. And I'm going to have IROC as, I'm going to have a variable in here. And that's okay because I want to solve the variable. I want to know where do they equal. So I want to do the inverse, the derivative here. And remember, f of x was inverse sine. So you probably need your little, is it a green sheet? 1 over so now where do those equal? So now we're back to algebra. Negative pi over 2 equals this where? AROC equals IROC where? That's all you're doing with MVT. AROC equals IROC and solve it. I'm probably going to cross multiply. Divide by negative pi and square both sides. Ugh. I'm going to subtract 1, so I got negative x squared equals. Now, I see that I'm fixing to have to take a square root. Y'all see that? I think that I am going to. Oh, let me go and divide by -1. I'm just going to leave it then. I'm going to go out on a limb and say that they did some crazy stuff factoring with this. Did they leave it like that? Oh, okay. What happens twice? Don't take the square root of each of those because that doesn't work. I was going to do a difference of 2 squares, but that's going to give me 2 different signs. It's not going to work. So I'm going to have to stay there. So It works because it meets the mean value theorem, and that is where they are the same. That one was tough. That was tough just because inverse trig. And inverse trig doesn't show up a whole lot, but it does show up. What else? I can't believe they left it like that. Oh, then they gave a. How did they give a decimal and they say this is no calculator? Whatever, bro. 23. This was a fun one. F of x equals x times the square root of 4 minus x. Local extrema, and where am I increasing and where am I decreasing? I think I'll look at my domain restriction first because I do have a radical, right? So what's the domain of this function? Well, 4 minus x has got to be greater than or equal to 0, right? Because it's a radical. So 4 minus x has got to be greater than or equal to 0. If I subtract 4, divide by -1, flip that sign, x is smaller than 4. Because whatever's under that radical has to be, I can't have a negative because I can't be an imaginary land. But it could be 0. So I now know I'm working with a domain smaller than 4. Smaller than or equal to 4. Let's find our critical points. Derivative here. Should I use product? That's really the only thing you can do. Root of the first times the second plus the first times derivative of the second. 1/2. 4 minus x to 1/2. Don't forget to chain. That was the biggest mistake. I can't believe that was the biggest mistake on y'all's test over and over and over again. Did not chain. Chain. This was the chain test and y'all didn't chain. All right, so don't forget to chain. Don't make me start singing the song. Okay, I know. Don't. I'm trying. Chain, chain, chain. We'll sing it as a chain roll, and then you'll never forget because you'll go, don't sing again, Miss Maggie. Okay. Oh, I know that y'all probably are all rested up, and I am sleep deprived and tired because I had a sick house. Okay. Minus x over the square root of, 2 times square root of 4 minus x. We need this to be a single fraction, right? Because we got to do, where does the top equal 0, where does the bottom equal 0? Remember all that? Gross. But here we go. I'm going to put this over 1. I'm going to give it this denominator. So 2 root 4 minus x, 2 root 4 minus x, which means that I am going to have 4 minus x over 2 root 4. 8 minus 2x minus x. Is that right? Yeah. 8 minus 3x over 2 times the square root of 4 minus x. Remember, this is derivative. So now I need to look for undefined points, and I need to look for points where it's 0. Top to 0 first. That's an easy one. 8/3. Bottom to 0 is a little bit harder. Really, I'm looking for where this is 0. Which is an endpoint, right? So remember, I'm smaller than, here's my derivative, here's my function. 4 is an endpoint, 8/3. So that's somewhere like here. Go with me? All right, let's sign test. If I put a 0 in. So that's this side. No, am I wrong? What's wrong? Sure. Positive? I get positive up top, positive on the bottom, so it looks like I'm positive. Is that what y'all got? I'm going to assume this is negative. 8 minus 9 would be negative up top, and then on the bottom, if I use 3, 4 minus 3, this one's positive, yeah. So negative.
I was trying to do those for the 4, and I was like,
oh, what, yeah. So increasing negative infinity to 8/3. Decreasing 8/3 to 4. What else did it ask me? Is that it? Increasing, decreasing. I do have a local max at 8/3 and a local min at 4. That very well could be an absolute max, but I would have to test my points and see. Increasing, decreasing. Oh, I can't make it. They are bracket. What did I tell y'all Friday? I know. I get mixed up. There's brackets. Okay. But the function does on increasing, decreasing. We will drill that right before the exam too, on what needs brackets and what needs parentheses, because they'll take points off on that. And 27. Oh my gosh, you pick all the nasty ones. I know, I'm picking. Okay. This is a calculator problem. Dang, we could have used our calculator for this other one too. That's what else I have to show y'all. I've shown y'all Inderiv on the calculator, right? Okay, I need to show y'all that again because on your calculator portion, none of y'all used it. And that's when you were supposed to use it. Okay, it didn't work. Okay, let me show you now. Wow, this is a great one to show you on. Because this is one where you have this whole big nasty function, right? And to find the derivative and all that. You don't necessarily, well, you do, because you want to find the derivative at a point, but I could also, I can also do x and x. Let me see. Okay. When y'all see this, you're going to go, oh my gosh. All right, so 27, look at this nasty, nasty equation, right? And since I'm trying to find local extrema and increasing and decreasing, what I really need to find is where my derivative is 0, right? Along with, because that's going to help me test. All right, so what I'm going to do is in y equals, I'm going to go ahead and type in this equation. Y equals, yep. Not this equation, but I'm yes, not the equation yet. Hit math and deriv. And I'm going to put an extra parentheses, and I'm going to type in this equation. There's one right over there on the radiator if you want one. All right, so yes, I'm gonna do a separate because normally, this is where you put your function or whatever it is. So I'm gonna do that. I just didn't. I guess you don't really need the extra parenthesis. I'd rather over parenthesis than under parenthesis. X to the third. What does yours look like? Type the function in there. Type the function. No, the D under the D should be an X. It should be D dx. Then you're going to type the equation. So I got x cubed minus 2x, sorry, minus 2 cosine x. I want it with respect to x. That's your d dx, right? And then, you have to tell it when x equals something. So I want the derivative at the, well, I don't want that here because I'm graphing it. So I want to do another x because I want x to equal x. So in other words, I want you to take the derivative with respect to x at x. I want to keep the x in there. And what's going to happen is it's going to graph my derivative function for me. I'm going to be able to tell positives. I'm going to be able to tell negatives. I'm going to be able to tell all that good stuff. Zeros, I know. It's been nice to know that, right? I'm sorry. All right, I'm going to do a zoom trig since I got a trig function in here. It takes a minute. Mine takes a long minute because it's an old calculator. But it's actually calculating the derivative. It does a rectangular approximation, which takes a forever time. Still even thinking some. Now I can calculate the zeros. So what y'all got? Did you go left and right? Left bound, right bound? Do it again. Come on, I crossed over. All right, so let's see. This is number 27. Yeah. So I got negative 1.126. You're doing what? Okay, let's do the other side. Left bound. This is some really high thinking your calculator's doing, so it takes it quite, see how sluggish it is? Mine's sluggish to even hit my spider over. And it takes forever for it to calculate because it's calculating the derivative first and then it's calculating the zero of the derivative. So it's doing a lot of calculating here for you. And then I got 0.5594. So let's think about this. Derivative function. Here are my two. Well, now my whole thing's sluggish. Okay. So now if you look, I'm positive, negative, positive, right? I don't have to plug in and test points. It's there for me. Positive, negative, positive. Positive, negative, positive. Oop. Increasing, decreasing, increasing. A lot easier. And since these are calculator problems, I can do that. If I went back to that other one that we just did, what was that? 23? What was it? X square root of 4 minus x. Let me just show you. X square root 4 minus x. Close that parentheses. I'm going to delete off everything else. Yep. This one I'm going to do just a normal zoom. Oh. X square root 4 minus x. There's my 8/3. 2 2/3, which was 8/3, right? 2 2/3, positive, negative. Look at all that work we did. 2 2/3, positive, negative. So if it's a calculator problem, let the calculator do that heavy lifting for you. Does that make sense? Did I learn you something with the calculator? I hope so, yeah. For 27, your zeros were different. How different? Been recording. I don't know why it just cut off. It might have been whenever I switched over to the calculator or something, but it's been working. That's the zeros they got. Did you type it in right? Are you in radians? That's why. Okay, try it now and it should work for you. All right, what else from your homework? Y'all okay? Sketch a differentiable function that has the given properties. A local minimum at 1, 1, and a local maximum at 3, 3. I would think that these would just be 1, 1. That's a minimum. So I'm going to be doing something like this here. And then at 3, 3, 2, 3. Maximum. Local maximum, something like that. So maybe something like this. That's continuous and differentiable. No corners, cusps, holes, jumps, anything like that. If I change it to a minimum at 1, 1 and 3, 3, so that's not saying it doesn't have other critical points, that's the only critical, it just says it's got to have those. So it's going to be a minimum here and here, so maybe something, somewhere it's got to come back up and do this. Ah! Sorry. Thank you. There we go. And then same thing with maximum. Oh, and I just erased it. I was doing part C. I was jumping ahead. That's why, y'all. Does that make sense? It's not, it's just, it's nothing. I think 40 is important, though. Let me just talk you through at least one part of 40, and then I'll stop with this for a while. F of 2 equals 3. That means it's got the point 2, 3. You have lots of these kind of things, but mostly they're analyzing. A lot of stuff is given to you. The derivative at 2 is 0. Tell me what that means. It's either a max or a min. More than likely, right? Whatever, but we know it's a horizontal tangent, but more than likely it's a max or a min. But it's a max or a min if, as long as it goes from increasing to decreasing or decreasing to increasing. So this is a maybe here, but definitely a horizontal tangent. So part A says that the derivative when the derivative is greater than 0 when x is less than 2, and the derivative is less than 0 when x is greater than 2. So I still think about this on a sign chart because I see everything on a sign chart. So at 2 is where it's changing. When x is smaller than 2, I'm the derivative, which tells me what the function is doing, right? When x is smaller than 2, the derivative is positive. So my function must be increasing, right? And when x is bigger than 2, so over here, the derivative is negative, which means I'm decreasing. So that means that at 2, which is this 0.23, that's going to be a what? A maximum. So my function is going to do something like this. Does that satisfy all the requirements? It has the 0.23. The derivative at 2 is 0 because it's a maximum. The derivative is positive when x is smaller than 2. Well, my slope is always positive. And the derivative is negative when it's bigger. It's always bigger. Yeah, okay. Y'all need a break? Y'all good? This is something really easy before I give you your test back to work on. I know. But this is getting us set up for integrals. Once we finish this chapter, we'll start drilling some midterm type review to get us through, because this is the last one on derivatives before we hit intervals, and it won't take us all that long to get through. Well, we got some tough stuff. I think maybe we'll stop. We might stop and test through 4.3, because 4.4 gets into optimization and some tough stuff. The toughest stuff with everything always comes at the end. Oh, and related rates. Let's do that since there's 4. Let's plan to test just a little half test through 4.3. But we're just on 4.2 right now, so we still got a little while. Instead of going all the way through 4, and then we'll hit 1 altogether on 4. All right, anyway, antiderivatives. If this is my function, this is my derivative, right? That's how we denote derivative. Antiderivatives are denoted by a capital X. And they are literally one step backwards from the derivative. So if you take the derivative of the antiderivative, you end up back at the function, right? So in sequential order, it would be antiderivative. Take the derivative, you get to the function. Take the derivative, you have the first derivative. Take the derivative. So if I keep taking derivatives, this is the order that I'm going in. So what we're going to do is we will be trying to take the derivative and get to the function, or the function and get to the antiderivative, essentially. We're using antiderivatives here to do it. It's just the backwards. That's all you need to know. But you'll see the capital F come up a lot, so just so you know exactly what that means. All right. Let's start easy. Let's just start X. Give me a possible F of X here. And I say possible because there could be more than one. Why is it so hard, right? Okay, Khalil says 2x. What's the derivative of 2x? Nope, that doesn't work. No, I'm glad you did it, though. We want to reason through. Okay, so let's think of another one. Look at you go. 1/2 x squared. What's the derivative? Yes, Caroline, we see you. X, right? Well, I said a possible one, so that's a possible one. Did I think of another one? Ah. All right, Henry says 1/3 x cubed. What's the derivative? X squared. Not x. Even simpler than what y'all are making it now. What's the derivative of constant? 0. In fact, I could put any constant tagged on the end of it. Do you agree? This is your plus a constant. You cannot ever forget whenever you're doing antiderivatives. Because technically, there's an infinite number of antiderivatives that I could have here that I could go backwards with. But let's go back to how you got this main part right here. So think, when we take a derivative, and you're so used, this is whenever it really gets confusing, y'all, because then you start forgetting, am I taking a derivative? Do I add? Do I subtract? What do I do again? All right, whenever I take derivative, right, let's think power rule. Power rule tells me to do what? Y'all can do this. Bring it around and subtract 1. So to go backwards, I'm going to do the opposite, okay? Instead of multiplying, what I'm going to do is I'm going to add 1 to the exponent, and then I'm going to, instead of multiplying, I'm going to divide by that. Divide by whatever you got there. So, for example, whatever this number is, yeah, that exponent plus 1. And then always plus c. Now this is for whenever we have these polynomials that it's easy to do this. This is just my power rule. Of course, some things I'm going to have to think through, like my trig functions and that kind of thing. I'm going to have to think backwards a little bit. But let's do a nice little easy polynomial. Let's go backwards on it. We might be correcting our test tomorrow. We might not be doing that today. Yeah. All right, so we did, you added 1, right? I'm going to add 1, add 1. This doesn't have 1, but really it does. Right? And then whatever this is, I'm going to bring around front and I'm going to divide. So 6 divided by 3 is 2x cubed minus 5, 2, right? Because there's this little imaginary 1. Yep. So, yeah. I missed it. Plus 2x plus c. Don't forget that plus c. You're gonna forget don't forget the plus c. Very important. You remember that rhapsody that I showed you at the beginning, and they talked about, you might not remember, they talked about the plus c. This is the plus c they always talked about. Yeah. I'll play it again halfway through, and then you'll understand half of it, and then I'll play it at the end, and you'll go, it's so genius. Like, it's really good. Okay. Are y'all okay there? It's not a hard concept. It's just hard to start getting in the process of thinking like that. Um, Here is the hard part though. Huh? That's just notation, so if you see it, like if they said f of x, if they said this was f of x, find the antiderivative, then this would be f of x. It's just notation to understand, that's all it is. This is a general antiderivative because it has the c in it, right? Sometimes we're asked to find the antiderivative, which is specific to a certain function. What that's doing is that's solving for the c. So in order to solve for the c, they'll have to give you a point with which to find. So let's say, for instance, we'll use this notation this time. Let's do negative cosine x. That passes through the point pi 3. This is the antiderivative. Antiderivative. As opposed to an antiderivative. So if I'm asked to find the antiderivative here, and this is f of x, this time I'm finding f of x. Okay, see the difference? See how I'm using that notation? All right, so I need to think backwards. What would give me negative cosine x? Negative sine x. Do you agree? Does everybody agree? And if you get confused, write it down and then go, what's the derivative of sine x? Negative, right? And okay, yeah, that's right. But I can't forget this, right? But now, after I find this with the plus c, I'm going to plug in this point given and solve for c. So that I've got that specific antiderivative and not just a general antiderivative. Well, what's the point? So 3, let's solve it for my constant. What's the sine of pi? All the way across, what's the y value across at 180 degrees? 0. So it doesn't matter this negative. So what's c? So what is the antiderivative here? Sine of pi is 0. I'm fixing to give you a challenge. Are y'all ready for this? You can always tell whenever I have more time to plan, right? Because I got everything all laid out and I'm ready to go, and then I'm not just okay. Thank you, Avery. I appreciate it. Monday was a little boring. First half of the day. Well, but my door, my room is like a revolving door, so I had about 30 minutes by myself. Find f of x. So this is f prime of x, right? So I want you to find f of x that goes through negative 6, 5. I'll give you a hint too. Don't use the power rule. I hope somebody sees this. Once you start seeing these, they start registering again. Well, you have to look at this. This is a pattern, not a pattern. Well, kind of a pattern. Look at your green sheet.
Oh, wait.
Yeah. It's hard. This is hard, especially when you finally get derivatives and you go, I got it, and then you go, okay, now do it backwards. You know it's hard. Who's got it? It is. You're exactly right. Good job. When you start seeing 1 over something like this, start thinking natural log. But you got to keep in mind chain rule, right? In the case of this one, if I do this, and I always, even now, I will write it and then I'll take the derivative and make sure, because I'm so much better forwards than backwards. So I'll go, okay, if I was asked to take the derivative of this, it's 1 over x plus 7, chain it. I just get 1 when I chain it, so I'm good to go. But I have to do C. You're exactly right. And since this asked me for the antiderivative and not an antiderivative, I have to plug this value in and I have to solve it for C. Y'all don't seem as excited about this as I am. That's okay. 5 equals natural log. This is working out nicely for you. This is the log of 1, which we know is 0. So my constant is C. So f of x must be the log x plus 7. Yeah, yes. Now, if whenever I started, I had called this f of x equals, then this would be big F. So it just depends on what you start with. All right, I'm going to stop, but I'm going to give you a little, I'm going to give you, it's not a lot tonight. Then I'm going to give you your test back. 217 to 218. I'm going to give you a hint on 11 before you start. 29 through 38 are easy. We actually just did a couple of those. And these are multiple choice. It's just 3 of them.